Imagine teaching a child to ride a bike. Too little help and they'll fall and become discouraged. Too much and they'll never learn to balance on their own. This delicate balance is much like the challenge of machine learning. We train our algorithms on data, hoping they'll learn patterns and make predictions. But like the eager parent, we must find the sweet spot between too little and too much guidance. This is where the concepts of underfitting and overfitting come into play. Underfitting is like trying to read a book in the dark. You might see faint shapes, but you can't make out the words or understand the story. In machine learning, underfitting occurs when our model is too simple to grasp the underlying patterns in the data. It's like trying to fit a straight line to a complex curve. It simply won't capture the nuances. Imagine trying to predict a student's test scores based only on how many hours they sleep. An underfit model might assume a simple linear relationship: more sleep equals higher scores. But this ignores other factors like study time, stress levels, and innate ability, leading to inaccurate predictions. Overfitting is like memorizing an entire textbook instead of understanding the concepts. You might ace the test on that specific book, but you won't be able to apply the knowledge to new problems. In machine learning, overfitting happens when our model becomes too complex and starts to memorize the training data instead of learning the general rules. It's like fitting a curve that passes through every single data point. It looks perfect on the training data but fails miserably on new unseen data. For example, let's say we use a massive, complex model to predict those same test scores, factoring in every detail about a student's life, from their favorite color to the number of steps they take each day. The model might achieve amazing accuracy on the training data but fail to predict scores for new students, as it has latched onto irrelevant details instead of the underlying factors influencing performance. Section 4. Finding balance, the bias-variance tradeoff. The struggle between underfitting and overfitting is often called the bias-variance tradeoff. Bias refers to the error introduced by oversimplifying our model, like assuming a linear relationship when it's not. Variance, on the other hand, refers to the error introduced by making our model too complex, like fitting a curve that goes through every data point. A good machine learning model needs to find a balance between bias and variance. We want a model that's complex enough to capture the underlying patterns in the data, but simple enough to generalize to new, unseen examples. Transformative technology.